All right, so the first thing that we always do when we're going through a problem like this is we're going to work on reducing, but we don't want to forget anything that we have canceled. So first off, we see if we can factor anything. Obviously the bottom we're not going to be able to factor, okay, but the top looks like we might be able to. I'm going to use some scratch up here. 2 times negative 3 gives me negative 6. I got a negative 5, so I'm looking for two numbers that multiply to get negative 6 and add to get negative 5. Well, that's just negative 6 and positive 1. So this can be factored. Okay. Now, if you factor it out, if you're not comfortable with these 2's out in front, I really recommend taking a look at how to factor with generic rectangles. It makes it really, really easy. And if I have time, I'll throw an example of that up. Anyway, this one should be 2x plus 1 times x minus 3 on the top. And on the bottom, we have x minus 4. Now, in this case, it doesn't look like we're going to have anything that we can cancel. Okay? Now, if you did have something you can cancel, that's when you would create a hole. And you can kind of see that this problem was set up with that in mind because there's no hole, place for a hole. Okay? So this one, it has no holes. Oh, can't spell. No holes. Okay? It doesn't have any holes because you create a hole when you have, like, for example, if there was x minus 4 and I had an x minus 4 on top, well, when x minus 4 is 0, it's undefined because I have a 0 in the denominator. If you can cancel a situation or a factor that makes x or the denominator 0, that creates a hole. Okay? So vertical asymptotes. Well, vertical asymptote is going to be created when our denominator becomes 0, and that's only from the simplified expression. Now, in this case, we didn't actually cancel anything, so we can just use the original expression or whatever. Okay? But you use the simplified expression when you are doing vertical asymptotes. So in this case, we're just going to see when x minus 4 is equal to 0. And that happens at x equals 4. So we will have a vertical asymptote at x equals 4. So again, that's giving us information of where we can and can't build our graph on the inside or on the middle of our graph. Now, horizontal asymptote. Okay. Well, in this case, we see that the degree, for the degrees, the numerator is bigger than the denominator. Okay. Meaning that the numerator will get big much faster than the denominator, and our graph will approach infinity. So there is no horizontal asymptote in this case. Yes?
Even if you simplify the expression, it's not
It-
the function.
It'll still, no matter what, even if you simplify, it'll still work out the same way as the original expression. And you can practice that, but if you're simplifying correctly, that shouldn't change. All right? Now, slant asymptote, well, that happens, okay, when the degree of the numerator is exactly 1 bigger than the degree of the denominator. Well, we can check to see if that's true. Well, the degree of our numerator is 1. Or I'm sorry, 2. Okay, it's to the second power. And then the denominator degree is 1. X is to the first power. So, this will have a slant asymptote, and the way we find the slant asymptote is we divide. So, in this case, x minus 4 is my factor, so my 0 is x equals 4. I'm going to take 4 and divide it into 2, -5, -3. Now, if you don't want to use synthetic division here, you can use long division. It'll work just the same. Yes, Shane?
Don't you only use synthetic division if the leading coefficient is 0 or 1?
It is.
2x squared?
The divisor of what you're dividing by. We're dividing by x minus 4.
Oh.
Okay? So that's what we're dividing by. Now, it's not even that, though. as I'd shown up there, I erased it. As long as you divide by the 0, it doesn't actually have to have a 1 as a coefficient. But if you're confused by that, just use long division. Okay? You're better off using long division because you can use it all the time. If you're if you're at all not sure about using synthetic division. So I drop the 2 down. 4 times 2 is 8. Get a 3. Then we get 12 here. And a 9. Now, the remainder doesn't matter. Okay? This was an x squared. We divided it by x. Now this is 2x plus 3. Y equals 2x plus 3 is our slant asymptote. So you divide it down, you get rid of the remainder doesn't matter, and what's remaining is your slant asymptote. And always keep in mind that when we're dividing, the whole idea is that x squared divided by x is x. It'll get you down to where you need to be. Okay? Now, to find our x-intercepts, well, whenever we're on the x-axis here, we know that y is equal to 0. So I'm just going to set y equal to 0, or in this case, f of x equal to 0. Our output is 0 on the x-axis. Okay, let me see if I can focus this up a little bit too. Now, if we do that, okay, one, you can remember that the whole fraction will be 0 if the numerator is equal to 0. But if you don't want to remember that, just remember we can write this as 0 over 1 is equal to 2x squared minus 5x minus 3 over, and actually I'm going to write this, we already factored this, so I'm going to go ahead and write it as a product of its factors. I'm going to use the slightly simplified, or actually just factored equation. It's 2x plus 1 times x minus 3 over x minus 4. Now we've set up a proportion. To solve a proportion, you use a cross product, and those cross products are equal. 0 times this is just 0, and that is equal to 1 times 2x plus 1 times x minus 3. Now the zero product property tells me that if 2x plus 1 is equal to 0, or if x minus 3 is equal to 0, then the whole thing equals 0. So both of these will give me a 0. So if I solve this one, I would get x is equal to negative 1/2. If I solve this one, I would get x is equal to 3. Those are my x-intercepts. So those are important values as well. Now y-intercepts, if I'm on the y-axis, then I know that x is equal to 0. Okay? So I'm simply going to set x equal to 0. I'm going to find f of 0. Well, that's just 2 times 0 squared minus 5 times 0 minus 3. Put that all over 0 minus 4. Well, these zeros are just going to cancel and go away, and we're left with negative 3 over negative 4, or just 3 over 4. Now we have tons of information. The only thing we're missing is maybe some additional points to clarify. But before we pick our additional points, let's put up all of our boundaries and critical points so we have an idea of what additional points we should pick. So the first one here is I'm going to go ahead and do our vertical asymptote. The vertical asymptote is just right here at x equals 4. So I go out to 1, 2, 3, 4, and I draw a dashed vertical line. Remember, you should always use a dashed line to show that it is a boundary. It is not part of the actual graph. Now, we also see here that we have a slant asymptote. I'm just going to switch up colors, but I'll still use a dashed line. And that slant asymptote is 2x plus 3. So I'm going to have a y-intercept here at 3, and then I'm going to go up 2 and over 1. Up 2 and over 1. I don't have a point at 3. all I did was I graphed y is equal to 2x plus 3. So if you graph that using slope-intercept form, then the y-intercept of our slant asymptote is at 3. Now, obviously, this graph, I probably should have used different units because we're going to end up off the graph here. But that's okay. We can figure it out. So we see here now that we have x-intercepts. We have x-intercepts at -1/2 and at 3. And we have a y-intercept at 3/4 right here. Now I think that actually over here, or through here, it's fairly obvious what our graph's going to look like. But we probably have some points to the right of our horizontal asymptote as well. Now it's going off the graph a little bit there. I probably should have picked some slightly different values for my units here, but it's not a big deal. Okay. Now, if we want, let's go ahead and pick one more value to the left of our horizontal asymptote. Okay, so we can do f of 2. If someone can calculate that out for me, that would be great. And then we could do a couple over to the right. So maybe f of 5, f of 6, okay, maybe f of 7. You can just do a few different values. Now, what you're going to find, and we're running out of time here slightly, is if you plug this in, I'm guessing for f of 2, you're going to get something in the neighborhood of, it'd probably be something in the neighborhood of 3. Okay. But basically, you're going to get a curve that as it travels farther to the left, it'll get closer and closer to your slant asymptote. And then it'll curve up, and it'll curve back down. And then as it travels down, it'll get closer and closer to your vertical asymptote. And then it'll mirror that up here. It'll be something to that effect. Okay? And I apologize that it went off the graph there and then we ran out of time. But this will be online. If you have additional questions, let me know.